for cache and save our money.
Imagine you have deployed a AI chatbot for your company. It's getting hundreds of users in a single day, and every single one of them at some point asks some version of same questions. And those questions are costing you per query, they are costing you some amount of money and some amount of average latency. So you are hitting the cost latency wall as you scale. How do I reset my password? Or maybe what's your business hour? Or can I get a refund every single time your application fires off call to LLMs? They burn through your tokens, waits 2 or 3 seconds, and charges you money. Imagine multiply to the thousands and millions depending upon your scale. That latency will stack up, your cost will explode, and your AI API rate limited will get hammered. User ask a question. Every single similar question that comes after it, regardless of exact word, could be an answer under 10 milliseconds at zero API cost. That's what we are going to learn how to build that system. This is what is called semantic caching. And by the end of this tutorial, you are going to understand it so deeply that you could explain it to anyone. Caching, semantic caching is, here's look at a visualization of a vector space. Here you can see if you see those dots, they are vectors in a three-dimensional space, and I have highlighted two vectors that represent happiness and joyfulness. And look at the sad vector. It's quite distant apart from the happy ones. So this is what semantically meaning. Although if you are going to put it through the traditional cache, they will be very different, three very different things. But on vector, in terms of semantics, they are very same things. So how we are measuring it? The most simplest way of doing things is cosine similarity, the angle of your intent. When two vectors are having same, what we are saying, when they are having very high cosine similarity, that means they are having same angle. That means they have a very same meaning. Larger angle, smaller cosine similarity will have a that means they have a different meaning. And the stack that we are going to use is Redis, and Redis has a very powerful tool setups and it's completely open source for you to use. We are going to use Redis for doing the semantic caching, and by just hearing the word Redis, you understand that it's probably going to be having to set up a database, and it's bit to feel it might be complex, but we'll make it very easy for you. And we are going to learn everything end to end, and everything end to end in your local system, so that way you will be able to produce it anywhere. The architecture that we will try to build here is user query. Now it will go through an embedding model, and then it goes to your Redis hierarchical index. This is a new search algorithm which is very effective. We are going to use that, and using that we are going to check if we are hitting the cache or missing the cache. If we are missing the cache, then we are going to call the language model. If we are um, uh, our hit is confirmed, then we'll return answer from cache. This is where the saving comes from in terms of cost and latency. But yeah, there is also a trade-off. Now there is a chance where two vectors must align, but they could have a very different intent. And so that we will also learn how we can balance between the high recall and precision. And generally for FAQs and chatbots, we tend to have higher recall. And for banking and legal system where accuracy matters, we'll tune our system specifically for those use cases. eh, and we'll have the vectors, cache, data, and there will be since it's going to be very centralized system, so it will have a very zero network hopping. We were able to get 250x faster results, very slow latency when it's coming from cache. We are going to do benchmarking. Our cost will, you'll see our cost getting reduced, and it will feel like very instant when you're comparing to a large language model. So let's build the instant AI with Redis. Let's start. Uh, let's first look at how we are going to set up our infra. I want to walk you through every line because understanding your infrastructure is not optional. When you are building production AI systems, if if you are like, you have to see that pain of building things. There's no way. You can probably get this done with OpenAI or Claude, but you'll not learn probably anything, and you will be just bloating your infrastructure. It's better to just for once see how things are being done. So yeah, let's create a Docker Compose YAML, which is going to make our infrastructure ready. So let's build it. You can obviously fast forward the codes. So we have our file, and let's first make our services. Services, what we are going to build here. Let's define. Let's do one thing. Let's start with the version of Docker Compose. Let's do that. So we need Redis, and let's pull the image. Redis, I remember Redis stack.lattice. So you can probably use a specific version, but your lattice is going to work. So in Redis stack, what we are going to pull is Redis itself, Redis search, Redis JSON, and Redis time series. So we must use this image. That's the standard image is not going to work here. There's this specific image which is going to work. So let's make give the container name. Container name Redis. Let's name it semantic. What we are doing, we are naming the container to make it easier to do execution later on. So we are good with containers. Let's do the ports mapping. So this standard Redis port, let's use that. It is 6379, and let's also map same 6379. And we Redis Insights also give their graphical user interface, so let's also map it 8001 to 8001, and we can obviously go to localhost 8001 in your browser and see. Let's make a volume. Redis data. Let's point our data. Uh, what we are doing is like persisting our cache in our disk. So if something bad's happen, then container restarts, we won't lose our data. Usually in production setting, you can put a mount EFS path here, EBS storage, that will work as well. And let's also part some environment variables. Redis args save 61. We can set log level. Let's only see warning for now. So what save 6001? It's save to disk every 60 seconds if at least one key changed. So this is how you should read. And log level warning, it reduces the noise in the Docker logs. And let's also configure the health check. I mean, we need to check if our infra is working fine. So let's make a test command. You can cmd open Redis CLI, and then just to ping. And let's set the interval of this test. So every 10 seconds, and you can time out in, let's say, 5 seconds, and it can retry. Do we need to do it? Let's try retries. Let's make 3 retries. Ensure what we are doing is ensuring Redis is actually ready before our app tries to connect it. And let's give this a volume. Redis data. Driver. Now notice we have health check. That is very important in production. Docker will tell you your container is up moment it start. Redis, but might be still initializing. So this health check is, it's actually it's telling that Redis is actually ready to accept connection before our Python codes tries to hit it. So now let's run docker compose up minus, let's see. Okay, container not allowed. Services dot additional property volume. Oh, sorry, it's S. Perfect. Redis data. Oh, container name. There must be some typo. EON TAINER. Hopefully it's working fine. It's going to pull the Redis stack for us. First time it's going to take some time. I'll believe from the next time it will be very faster. Perfect. I just visited localhost 8001 and we can see submit. We can see our clean, nice Redis dashboard. So this is what is called Redis Insights. It's a full graphical user interface for your Redis instance. We can see every key we store, every vector, every cached entry. This will be incredibly useful when we get to our demo portion. So for now, let's get going into the code. Let's open another terminal and let's give it environment. Perfect. And now let's start building our code base. So let's make a source directory, and inside that let's first make a benchmark. And let's go raw.py. Here we will baseline, where first we'll try what happens if we don't use no caching. We'll just measure the raw output, and let's go ahead and also build 02 with cache. And then also we'll make an agentic flow that will leverage both of these things. And yeah, for now I think that looks good. So let's add our dependency. I use UV. You can use pip as well, no problem. So you'll need to install Redis VL, Redis Vector Library. This is code for caching, and I'm going to use LangGraph as the agentic framework. And let's use Google Gemini so that if, I mean it's to certain limit it's free. Let's take the advantage of that, and so that everyone can follow this lecture for free. Gen AI, and we'll also obviously Python. And let's also make a CLI. We'll try to make a CLI. So we'll do some computation. So let's also better to bring the numpy. Perfect. Let's open our pyproject.toml, and I can see we have pretty much everything that we wanted. And let's try to build the cache-based baseline. We need to know how slow and expensive raw API results. So let's open our first script. The purpose here is to measure a performance with zero caching. So let's start building. Import time was from .env port load. I'm not getting feedback, so probably does this have Python? I believe my VS Code has just decided to uninstall the Python. Let me just get rid of this quickly. Let's do developer reload window. I hope our container is still running. It's done. So from .env import load.env. Great, I'm getting feedback. From LangChain Generative AI, let's import chat Google Generative AI, and let's use rich.console. Let's import console from rich. Let's also get the table. Be helpful in seeing the results. Let's load our environment variables. And let's initialize the console. All right, so before moving there, let's go and get our Google Gemini key. Let's go to Gemini, Google AI Studio, API, and let's visit, get started, get, get the API key, and let's create new API key. Let's make it Redis. We can select one of the project, and that's pretty much. We can take the Redis key. I am going to invalidate this, so not a problem. .env Google API key. Let's paste that. Perfect. We are good with it. Let's initialize our Gemini model now. LLM equals to chat Google Generative AI, and then let's build the model, and let's go with Gemini to Gemini 1. No, let's go 2.5 hyphen flash, and let's put temperature. Temperature, let's put that to 0, and let's put our Google API key. The screw key equals to os dot get env, and let's put what was the name. Let's go. All right. As per I believe, let's also check input cost per token, and what I believe it is $0.075 per 1 million. Makes it million. Oops. Yeah, per 1 million. And output per token, that's about 30 cents. And let's make
It's, I believe, let's take also an average just to understand the statistic. I think per transaction we can assume 50 input. You can play with those numbers to understand the math, but this is just to make the point. You can get more detailed into the specifics. Let's define a function that's going to calculate the cost. So input, it takes token, output, tokens. We can just return. So it's going to be the input token into input cost per token plus that's just multiplication. Nothing fancy here. Output cost per token. Perfect. So now let's prepare our test queries. And what I'll do, uh, I'll try to make them semantically similar group. So let's make some test queries. QUERIS. Suppose you are running an educational platform and you are delivering a lecture on Dockers. So this could be a simple question. How do I start a Docker container? And possible semantic question would be what commands runs a Docker container? CONTAINER. So do you see? Just see that these two strings are same. So and their answers are also same. Like that is the whole point. So let's go ahead and let's present this data beautifully. Let's me make a table title raw Gemini cache baseline dot add columns. Let's first put query and we can give it a style wide width, let's give 40 pixels. So it's essentially now the terminal UI looks really good. So that's what I'm doing. And let's measure the latency and see why. That will be in milliseconds. And we can justify it to the right. Can style, let's put red. Table dot add column. Let's add estimated cost. Once we'll get, we'll also calculate the actual cost. And that will be justified. Let's also make it to the right. And let's style this to be yellow. add column, token input, output. Let's justify. So let's calculate also total time for running them and total cost as well. So let's go for query in test queries. We'll iterate over them and let's start time.perf count. Perf counter, and then we'll get the response. LLM.invoke, and then we'll get query. Let me do one thing. Let's also calculate here time dot perfect counter, and then we can subtract latency in milliseconds. Thousand cost calculate cost. For now, let's put the average input. Let's put the average output token. So basically I just wanted to see first, is everything working fine, and we can also add to the total time latency milliseconds. Total cost is equals to cost, and then we can table dot add row, and then we can just put query. Let's put first 30 characters plus, let's format if it is flowing, if length of query is greater than 30, and if it is less than that, we'll just we can keep this as it is. Let's format our latency milliseconds. Let's format floating, that's in the milliseconds, and let's cost, it's going to be somewhere cost 6f. That'll do the work. And then let's go with the average input token divided by average output token, just to check token in out. I mean, it won't actually divide, but they'll just do the formatting. And let's go console dot print table, and then just see if this code works. So uv run src 01 benchmark.py. Did you mean temperature? Yes, sorry. made a typo. And now let's see. It's not compatible with Python 3.1 or greater. Oh, so yeah, perfect. I just wanted to see. Let's put a break here. I just wanted to first see how how to pass our response. Is it coming correctly or not? Let's run it. You can see it's making an inference. Okay, so what do we have here is the content, and we are actually looking for the token, yeah, usage metadata. So we'll go there. It will be response dot usage metadata, and from there we'll try to get input tokens, and then same thing but for output tokens. All right, now this is going to do a exact calculation for us. Let's do same thing here. Let's print them out. Control C, Control V. We don't need that placeholders anymore. Perfect. And now let's remove this breakpoint and let's get rid of this print statement. Hopefully we will see our table getting populated with the values that we are looking for. Oops, please. Yeah, that's what it was trying to show me. Now looking at this, okay, so it says cost calculation metadata does not have this key, but I think it has. Usage metadata. Let's do one thing. Let's print this again. Alright, can click the to JSON, and we can indent. I believe they have a to JSON method to it. Okay. So, dot content. Let's go. Let's go open this in a JSON viewer. Then it will make sense. Let's see if we are going to get the output. We'll properly see how things went. Yeah, it's going to take some time. That's the point. We are trying to save exactly those latency time. So it takes 15 seconds, 10 seconds, and hence we send 9 tokens and we took this much output. Although this should be the only cost because essentially we are asking the same question. Look at those time that we have spent. So let's fix that. In the next module, we are going to do everything same. We'll try to keep uh, same code, but what we'll do this time we are going to use the semantic caching. So let's go and copy. Most of the code is going to be same. I'll make the changes wherever it's required. So let's bring few more dependencies which we want. So let's view from Redis dot extensions dot cache dot llm dot let's import semantic cache, and from LangChain and let's also bring an embedding model because we have to make an embedding out of that. And let's also uh, from rich dot panel, let's import panel, and that's pretty much same thing. So why we bring these two new things? Because obviously this time we are going to try with cache, and now we will try to, since we are using semantic cache, the heart of the system depends on the embedding of how well we have generated that. And so let's try to first bring our embedding. We have an LLM, let's define an embedding. It's Google Generative AI embedding, and we can define model slash text hyphen embedding. Let's go with 04, and then we can just use same Google API. Perfect. I believe our embedding is ready. And then we can use same model. And now let's build up our cache. CACHE cache is semantic cache, and let's give it a name of V1. So this is going to become the Redis key prefix. Everything will start with this. Now let's point to the Redis URL, and it is red this protocol /local host 637M or a port that you have configured during your local setup. Now there are some critical parameters, which is the distance threshold. Let's keep it 0.12 or so I'll give you an idea. 0.0 means perfect match we are looking for. 0.1 to 10 we are looking for close enough, same intent, and 1 is completely different. So lower, stricter, fewer false positive, and we will have a more misses over there. Higher will lose, I mean, it's going to have more hits, but risk of getting the wrong answers. So now, what is going to be our vectorizer? The one which we have defined above. It tells RedisVL which model to use for creating embedding. Must be consistent. This should be same model for storage and lookup as well. And now we can create a ripper function. Let's call it def ask with cache, and it's going to take the query. That's tr, and it's going to return the dictionary. What it's going ask, we ask AI question with semantic cache. It returns dictionary, source, answer, latency, and vector distance. So this is how the format is. So let's start a timer. Like as soon as we enter in this function, let's measure it. So cache response, and we can see cache dot check will pass prompt as query. Now if cache result, if we are able to see the cache result, then we can end. First of all, because we are doing benchmarking, so let's see how much time it took, and then let's return a lot of things from here, and let's make this as source to identify whether we are hitting cache or not. Cache hit, and then let's answer is the hit. Oh, first let's also store result. Hit is equal to cache response. Let's take the topmost match. So hit dot cons, we can create time in milliseconds. Minus star in 1000, and we can have a distance. Hit vector and then API cost. In that case will be 0 because we know it. We haven't called the LLM. That's cool. Now this is a step 1 if we are hitting the cache, but there can be a chance where you are missing the cache. So in that case, let's llm dot invoke. So same thing that we did over there, and we can pass our query, and once we have our answer, response dot I think it's content, and we can store in our cache here with an optional time to live. So let me show you what I'm trying to say here. So cache dot store, and we can say prompt is query for this input, response is answer, and the time to live is 3600. So this means this particular entry should get expired after 1 hour, and after doing this we can measure our end time dot perf counter, and then we can just do pretty much the same return, where is going to be Gemini API, and in that case the answer will be just the answer, and it's going to be same. We probably don't need, there's no sense of giving a distance, but yes, the cost will be cost is something that we need to keep a track of. So I think we can copy that same code. Let's go back there. If response has this and this input and output, we'll get that, and let's do the calculation. So input token, input cost per token plus output token, output cost per token. Perfect. So we have kind of reused things that we have done previously. Perfect. Now let's try to run our benchmark. Yeah. And here we are going to benchmark to see how distance are hit versus miss. So we expect this to be a hit, and same way P1, B2, and this just the same thing. And this is going into query asking with the cache if it's a cache hit. Let's go check. Yeah, if this the cache, and then we are doing some formatting over there, and then the baseline Gemini. This experiment we have seen that we are getting about results in 10 seconds. So let's keep that as the baseline. The experiment we just run, you can see one came in 15 and one came in 10 seconds. So let's hope to see the same kind of results, and I think we are pretty much good. So let's call Python src0 with cache. Line number 23. Must provide a vectorizer class for now. But I believe there must be some way around for this. For now, let's from Redis dot utils dot let's pass the vectorizer, and this is going to download a king face. To install, we need to have this sentence transformer. Let's add it. Hope we don't see any error. I will be very interesting to see how the distance among the queries that we have. How do I start a Docker container? What commands to run Docker container? Docker container sentence transformer got expected where model ID. So what does it expect? Model. Hopefully that's the last. Okay, it's downloaded. It's downloading the model. All right. Semantic cache benchmarking is getting start. Let's see. Actually very excited. I probably want to see us saving costs over here. So in theory, it should work. Let's see practically. Great. You can see over here that we have in fact saved our cost and the latency. Cache hit. First, how do I cook uh, medium rare? Then next time it got it from for cache and save our money. So that's actually very interesting to see. So that's the idea. Like now